Now that we have an idea of what a confidence interval is, let's look at how to actually calculate one. I'm going to start with confidence intervals for the mean, how to estimate the mean. And I'm going to show how to do this by hand using summary statistics like the mean and standard deviation of the sample, as well as how to use R if I have a set of data. In order to use this method, I'm going to need one of two things to be true. I'm either going to need my distribution to be normally distributed, or I'm going to need a sample size greater than or equal to 30. I'm going to use Tn-1 to represent my t-distribution with n-1 degrees of freedom. And in the previous video, I said that we would look at the sample size minus the mean divided by the standard deviation. However, central limit theorem actually tells us that the standard deviation is the original sample standard deviation divided by the square root of the sample size. So this is the idea of what I need to use. In this case, I'm going to know x bar, I'm going to know s, and I'm going to know n, and I'm trying to figure out what mu is. I'm trying to determine what this population is. So we want to solve for mu, and keeping in mind that this t-value is generally positive, but whenever we build these confidence intervals, we need a positive value as well as a negative value. So when we do this, we have this x bar minus Tn-1 of alpha over 2 times s over the square root of n, and then x bar plus Tn-1 alpha over 2 s over the square root of n. And what this tells us is that the mean is going to be somewhere between these two values. So let's look at an example of computing this by hand. A random sample of 56 cotton pieces gave average percent elongation of x bar equal to 8.17 and sample standard deviation of s equal to 1.42. I want to construct a 95% confidence interval for mu, the population percent elongation. So let's try to do this by hand. In order to do this by hand, we need to know four numbers. The first is the sample mean, x bar, which is 8.17. The second is my sample standard deviation, which is 1.42. The third, my sample size, 56, which is greater than 30, so we can use this distribution. The last thing I need is the value of Tn-1 of alpha over 2. So this one's a little bit trickier. We do want a 95% confidence interval, so that tells me alpha is equal to 0.05. So alpha over 2 would be 0.025. The idea is if I have this distribution, I'm trying to find these values here that would give 95% of the data in here. So that tells me there's 5% not shaded, 0.025 in this tail, and 0.025 in this tail. So in order to actually find the value of t, we could use two options. The first option is there are tables of t values. My degrees of freedom would be 55 since it's n-1, and I would want a 95% confidence interval. In the table, we would just go to the 95% confidence interval and the 55 degrees of freedom and read the appropriate value. Or we could use R. In this case, we would use the QT command. What we actually want is this value here, which has 95 and then percent of the data and then 2.5%. So we actually need 0.975 with 55 degrees of freedom. And we get a value of 0.2004. From there, I'm going to find the value of TS square root of n. So 0.2004 times 1.42 over the square root of 56. And when I do that, I get roughly 0.38. So my actual confidence interval would be my sample mean minus 0.38 and my sample mean plus 0.38. That would give me 7.79 and 8.55. So there's a 95% chance that the actual population mean is somewhere between 7.79 and 8.55. So now that I did this by hand, let's look at how to solve this problem on R. Now that I've solved this by hand, let's look at how to solve this problem using R. If we want to do this in R or RStudio, we need to essentially type in the formula directly in. So we have our mean of x, so our x bar, plus or minus this qt of 1 minus alpha over 2, degrees of freedom equals to length of x minus 1. This is our t value. We're going to multiply by the standard deviation divided by the square root of the sample size. So let's look at doing this example that we just did on RStudio. Here I have RStudio. So if we type it in, we need our sample mean minus the t value, which came from qt. Inside of this, we need to put 1 minus alpha over 2. Since we wanted a 95% confidence interval, alpha was 0.05, the opposite of 0.95. We had 55 degrees of freedom since our sample size was 56. We multiply by our standard deviation, 1.42, divided by the square root of the sample size, 56. And if we run this, we do get our lower bound, 7.79. For the upper bound, we use the exact same command, except we change this minus sign to a plus sign. And then we can run that. And that gives us our upper limit, 8.55. And this is exactly what we got when we did the computations. So we do have the option of using RStudio or doing these by hand. This method of using RStudio is going to be used whenever we are given our population mean or population standard deviation, but we might just be given a set of values that we actually have to find the mean and standard deviation for. And in that case, it's actually a little bit easier to use RStudio. Let's look at this example here. The Sharpie impact test determines the amount of energy, in joules, absorbed by a material during fracture. A random sample of 16 test specimens of a particular metal yields these measurements here. And I want to construct a 95% confidence interval for the population mean amount of energy absorbed during a fracture. If we wanted to do this method by hand, we would need to start by finding the mean and standard deviation of these data values, and then using the method we used in the previous example, but that's very long, and it's not necessary if we have access to RStudio. In RStudio, we just need this command CONFINT for confidence interval. We do LM of x, where x is a vector containing all of the data points, a tilde 1, and then we give our confidence level. So let's show how to do this in RStudio. So here I have RStudio, and I went ahead and created this vector that I called x that contained all of the data points provided to me in this example. So I can run and save that. So we use our command confidence interval, CONFINT, for the confidence in the interval of LM of x tilde 1, since my vector is saved as x. And then we need our level. Since we wanted a 99% confidence interval, we have that our level is equal to 0.99. And then we can run this command, and we get that our confidence interval is 2.92 to 3.92. So the true population mean is somewhere between 2.92 and 3.92 with a 99% certainty.